All right, so let's proceed from where we left off the last time. So the last time we were here, we were discussing the mercury barometer, which is used to measure the um, the atmospheric pressure. All right, and I won't go through how this works. So let me skip to the next. Oh, okay. So this is just an example of how we can convert from one unit of pressure to another. It says here that a Canadian weather report gives the atmospheric pressure as 100.2 kilopascals. What is the pressure expressed in torr? So the relationship between kilopascals and torr is 101.325 kilopascals is equal to 760 torr. All right. So basically, the way we'd set this up is 100.2 kilopascals will be multiplied by 760 torr over 101.325 kilopascals. So that these units will cancel out, the kilopascal units will cancel out. And all we have to do is the number crunching, which is 100.2 times 760 divided by 101.325. And, oh gosh, I did something wrong. Let me do this again. 100.2 times 760 divided by 101.325. So according to my calculation, this works out to be equal to 752, actually 751.6 torr. It should be a 7. All right, so that's basically it. A normal type of conversion going from one unit to another. All right. Okay. So that's a relatively simple example. Okay, so the next type of instrument we're going to talk about are what are known as manometers, right? And this is used to measure the pressure of a sample of gas. So if you have a gas trapped in some sort of container, then this is the instrument that you would use to measure the pressure. So that is different from the barometer, which is used to measure atmospheric pressure, all right? This is just used to measure the pressure of a gas in a container, right? And what is used in this particular instrument is a U-shaped tube. And basically, as stated here, the pressure is measured using the difference in the mercury heights in the arms, in the two arms of the U-shaped tube, all right? So this is what we call a closed-end manometer, right? So this is a U-shaped tube, which will contain the mercury, and one end is sealed in this case, the other end is connected to your container, which has a gas. So you turn this on, the gas flows through, and it basically hits the surface here, and it pushes the surface down here and pushes the mercury level on the other side up. And basically the difference in the mercury levels between the two tubes or the two parts of the U-shaped tube, that would be equal to the pressure of the gas exerted here. The assumption, of course, is that there's a vacuum here, which is a pretty good assumption because even though there may be some mercury vapor here, the pressure here will be very, very low, effectively zero. So therefore, basically, the pressure that is exerted here would simply be the height difference between the two mercury levels on both sides of the U-shaped tube. All right. Now, so therefore, you can get a direct measurement of the pressure of the gas in millimeters mercury, right? All you have to do is measure that height difference, and that's it, right? Now, if you're using some other liquid, right, then to calculate the pressure in pascals, then you'd use this equation right here, right? Pressure is equal to G times D times H. So let me explain what each of these terms mean. G is a term, I don't know how many of you have done physics, but G is a term called the acceleration due to gravity, right? That's basically the acceleration of an object. If I were to release, for example, this pen and it falls to the earth, it accelerates as it goes down, right? And you can actually measure that acceleration. And that's true for pretty much every falling object. If you don't take into account, air, what do you call it now, viscosity effects, right? So the value for G is given right here. It's 9.8 meters per second squared, all right? Now D, in this particular context, would be the density of the liquid, right? H would be the depth below the surface of the liquid in meters, all right? And that H here would be the same thing as this delta H right here, right? So you can measure the pressure in pascals if you use G here, the density of the liquid here, and the height of the, or the depth below the surface of the liquid here, all right? So that's a formula that you can use to calculate the pressure, if the pressure is in pascals. I should specify and point out that in order for the pressure to be expressed in pascals, G would have to be expressed in meters per second squared. The density would have to be expressed in kilograms per meters cubed, and the depth below the surface would have to be expressed in meters, right? So once you have those units in place, then when you put the numbers in, then the pressure would be expressed in pascals. All right. Now, what I just showed you is what we call a closed-end manometer, but we can have what are known as open-ended manometers, right? And these can also be used to measure the pressure of the gas, but you have to take into account the atmospheric pressure. So I'm just going to explain how each of these works, right? Now, the difference, it's the same setup for both sides, for here and here. The difference between them is that the mercury level on this side here would be lower than compared to here, and it's switched in the other case where the mercury level here is lower compared to the mercury level here, which is directly connected to the container with the gas. All right, so let me deal with this setup first. So basically, you turn this on, gas flows, and then hits here, and then it forces the mercury level down, forces this up, right? So therefore, you have to take into account two things. One, the pressure of the gas that is exerted on the surface right here, and the atmospheric pressure, right? Because this is open to the atmosphere. So therefore, the atmospheric pressure will be acting on the surface here. So P bar, in some textbooks, they call this a barometric pressure, atmospheric pressure, same thing, right? So P bar is acting here, P gas is acting here. So obviously, what this means is that the pressure of the gas would be greater than the barometric pressure. And that difference would be the delta H right here, all right? So therefore, we can say that P gas, which is the pressure exerted here, would be equal to the barometric pressure plus delta H, right? So basically, if you know what the barometric pressure is, and if you can measure delta H, you can easily determine what the pressure of the gas is, all right? So that's what happens in this case. Now, if the situation is flipped where the barometric pressure is actually greater than the pressure of the gas, then basically what that means is that the difference between these two, again, would be equal to delta H, which means that the barometric pressure would be equal to the pressure of the gas plus delta H, all right? And therefore, as a result, we can again calculate the pressure of the gas. In this case, the pressure of the gas, the pressure exerted by the gas, would be equal to the difference between the barometric pressure, P bar, and the height difference between the two mercury levels on either side of the U-shaped tube, all right? And in this particular case, there's an example here. It says for part B, which is this right here, what is the pressure of the gas if delta H is 100 millimeters and P bar is 760 millimeters? So basically what you have to do is rearrange this to get P gas is equal to P bar minus delta H, which would be, in this case, 760 millimeters mercury minus 100 millimeters mercury. And let me just go right here and write down the answer, which is 660 millimeters mercury, and that's it. All right, so that's basically how you can determine the pressure of a gas using an open-end manometer. Okay, any questions about this? Any questions? Okay, now the next slide is dealing with comparing water to mercury. Now, you might be wondering, why is it that we use mercury in all the instruments that we were talking about before? Why is it that mercury is the liquid of choice and not something which would be far cheaper like water, right? Because mercury is expensive, right? Well, this question actually illustrates the reason why. So let's look at this question. It says, calculate the height of a column of water. It gives the density, and then it says that exerts the same pressure as a column of mercury, and it gives a density here, 760 millimeters high. So therefore, what they're asking for is the height of the mercury column that would exert the same pressure as a 760 millimeter column of, I'm sorry, I think I misspoke. The height of a column of water that would exert the same pressure as a 760 millimeter high column of mercury, right? So therefore, and this is a recording, the writing that you see here is because I was recording this. So I'm just going to go through the steps here. So the first thing I'll do is write down the equation which relates the pressure that is exerted by a liquid column and the height, the acceleration due to gravity, and the density. We saw this equation earlier, right? Also, because it says that both the water and the mercury exerts the same pressure, I'm just going to set PW, which is the pressure exerted by the water column, is equal to P mercury, right? So what I'm going to do now, going from here to down here, is write down this expression for P water and this same expression for P mercury. So for P water, that would be the height of the water column times G times the density of the water, and that would be equal to the height of the mercury column times G times the density of the mercury column, right? And then now to isolate the height of the water column on this side, I would divide both sides by the density of water. So that's why we have density of water dividing here and that at the same time. These two would cancel out. So you'll be left with, and the G's, by the way, will cancel out. The acceleration due to gravity will cancel out as well, right? So you're going to end up with the formula for the height of the water column being equal to the height of the mercury column times the density of the mercury column divided by the density of water. And then all I have to do is put the numbers in. The height of the mercury column is 760 millimeters times the density of the mercury column divided by the density of water. And you're going to get the answer here, which is 10,300 millimeters, all right? Which is, if you were to use water instead of mercury, then you're going to need a tube, which would be at least that tall. So the 10,300 millimeters would be the same thing as 10.3 meters, all right? And just to give you an idea as to what 10.3 meters look like, my height is just under 2 meters, right? So if you think of a tube that is like, what, 5 times my height, would be very inconvenient, all right? And that is the reason why mercury is used, because mercury has a higher density, so therefore a smaller tube would be used in order to measure the pressure in instruments like a manometer or what's the other one? Barometer, all right? Okay, so this is just illustrating or explaining why mercury is a liquid of choice, even though it's more expensive. But you know, if we were to use water, then we'd have to use like a tube that long couldn't fit into this room if we were to use water. Okay, so with that said, let's talk about some laws concerning the behavior of gases. And the first one is Boyle's law, which relates the pressure of a gas to its volume. And the law can be stated in words, but it can also be stated mathematically. So in words, we can state it as, for a fixed amount of gas at a constant temperature, the volume of the gas varies inversely with its pressure. So what this is saying is that there's an inverse relationship with the pressure, between the pressure and the volume of a gas, right? So basically what they're saying is that if you were to, let's say, reduce the volume by half, then correspondingly the pressure will be doubled. If you reduce the volume by a third, then the pressure would be tripled, all right? But keep in mind that in order for this to be true, the amount of gas has to be fixed and the temperature has to be constant, right? So those two things have to be constant in order for you to observe that relationship. Another way of stating this law is that, again, for a fixed amount of gas at a constant temperature, the product of the pressure and the volume is a constant, right? And for those of you who are enrolled in my lab, which I think is all of you, or most of you, there's one experiment that we're going to do. Actually, we're going to see this law work, and it's one of my favorite experiments, right? You're going to actually see the fact that the pressure times the volume is constant, right? For a gas that is trapped in a container. So mathematically speaking, we can write it like this. PV is equal to a constant, or P initial times V initial is equal to P final times V final, right? Or the way I prefer to express it, Same thing, but just a different ways of writing it down. P1 V1 is equal to P2 V2, right? So that basically just is stating the fact that the product of the pressure and volume is equal to a constant. Now, graphically speaking, we can see how this law works. So this graph here is showing you the pressure plotted versus the volume. In fact, again, for that experiment that you guys will be doing, we'll be actually seeing this law, this graph, right? So if you plot the pressure here versus the volume, we can see how this law works. So let's say you're starting from here, where the pressure is 4 atmospheres and the volume is 1 volume unit, right? If you were to double the volume, then the pressure of the gas would be reduced by half, from 4 to 2. And then if you double it some more, the pressure will be reduced further by another half, from 2 to 1, and so on, right? So basically that shows you the inverse relationship between pressure and volume. Now, if you were to plot, instead of pressure here, 1 over the pressure versus the volume, you're going to get a straight line relationship. And the reason why that is so, if you were to look at PV is equal to a constant, right? And then you, how am I going to do this? Let's say you say that, I'm trying to think of a nice way of, okay, let's say V is equal to K over P, right? Okay. Or another way of stating this is V over K is equal to 1 over P, right? Let's say that I say that K is a constant, but I can express it in terms of another constant, which would be K prime V, right? So this would be 1 over P versus K prime V, right? So if you think of the equation of a straight line, this would be the y-axis or the y term, this would be the x, and K would be the m, right? Which would be the slope of the graph, right? So basically, if you plot 1 over P versus V, 1 over P on the y-axis and V on the x-axis, you're going to get a straight line graph. And again, this is something that you're going to observe when you get to doing that experiment, right? So that is another graphical representation of the relationship between the pressure of a gas and the volume, all right? And we can explain, of course, based on the kinetic molecular theory, why we observe this trend, right? And this is pictorially represented here, right? If you increase the volume of the gas, that means that the molecules will have more space to move around, and therefore the molecules will not hit the walls of the container as frequently, right? And therefore the pressure exerted on the inner walls of the container would be lowered as a result. And therefore that's why when you increase the volume, the pressure will be reduced proportionally. Okay, so let's look at this example. It talks about a helium-filled party balloon that has a volume of 4.50 liters at sea level, where the atmospheric pressure is 748 torr. It says, assuming that the temperature remains constant, what will be the volume of the balloon when it is taken to a mountain resort at an altitude of 2,500 meters, where the atmospheric pressure is 557 torr? So you should immediately recognize that this is a Boyle's law question, right? And when you get a question expressed this way, it's very important that you try to identify the different terms, all right? Now, Boyle's law says that P1 V1 is equal to P2 V2, right? So basically, you need to find out what each of these terms represent, or which of these numbers represent each of these terms, right? So I can immediately see that 4.50 liters would be V1, the 748 would be V2, I'm sorry, P1, and the 557 torr would be P2. And the question is asking for the atmospheric pressure, the volume at P2, so that's V2, right? That's what the question is asking for. So therefore, you'd have to rearrange this equation here algebraically to get an expression for V2, which would be P1 V1 over P2. And then all you have to do is put the numbers in. So P1 would be 748 torr. V1 would be 4.50 liters divided by P2, which would be 557 torr. And then you do your number crunching. So 748 times 4.5 divided by 557. And according to my calculations, I got 6.04. And the units here would be liters because the 2 units will cancel out. And that's it. And that's how you do that calculation. And let me just say, and you probably know this already, but I'll just say it anyway. Whenever you're using the Boyle's law equation, it doesn't matter what the pressure units are, and it doesn't matter what the volume units are, as long as they're the same on both sides, right? So the units for P1 and P2 must be the same, right? And the units for V1 and V2 must be the same, right? Very important, because you could be given a question where, let's say V1 is given in liters and V2 is given in, I don't know, gallons, let's say. Then you either have to convert the liter value to gallon value or vice versa before you plug them into that equation in order for you to solve that particular problem, right? So it doesn't matter what the units are for the different terms, but they must be the same on both sides for the same type of measurement, all right? Okay, any questions about this one? Any questions? Any questions? All right. Another law we're going to talk about is Charles' law. And this law relates the temperature of a gas to its volume. And again, this law can be stated in words. As you can see here, the volume of a fixed amount of gas at a constant pressure is directly proportional to, and this is very important, is directly proportional to its Kelvin temperature, right? So this law is more specific in terms of the units in which, in this case, the temperature must be expressed. The temperature must be expressed in Kelvin. And we're going to get into the reason why that is so. So this is the way of expressing this law in words. So this brings us now to the concept of absolute zero, right? And this is the temperature obtained as a result of extrapolating the plot of volume versus temperature to a situation where the volume is predicted to be, what happens when the volume of a gas is predicted to be zero? What that means is basically that the gas molecules will have no kinetic energy. There are 3 forms of kinetic energy that molecules will have. You have translational, you have rotational, and you have vibrational. So if you were to reduce the temperature to absolute zero, quote unquote, then basically these type of modes of motion would not exist, all right? And it turns out that the absolute zero is equal to minus 273.15 degrees Celsius, all right? So therefore, this brings up, this is the reason why, excuse me, why the Kelvin unit was invented, right? Basically what the powers that be decided was that 0 Kelvin is going to be equal to minus 273 degrees Celsius, right? So the relationship between, and I think I gave you this equation already, the relationship between the Kelvin scale and the Celsius scale is that temperature in Kelvin is equal to temperature in Celsius plus 273 Kelvin. And what I'm trying to remember here is the units, which would be Kelvin here over degrees Celsius. All right. So that's a relationship between the Kelvin and the Celsius scale. All right. Okay. So, excuse me. So let's look at a plot. Oh, before I do that, I should also talk about another way of stating this equation or this law mathematically, and that is V1 over T1 is equal to V2 over T2. All right. Or I could say V over T is equal to K. But this one is more useful because basically if you know 3 of these terms, you can calculate the 4th one, all right? Okay, now let me show you how we arrive at this whole concept of absolute zero. So what is shown here is what happens when you plot the volume of a gas versus a temperature expressed in degrees Celsius, right? Now, what will happen is that as you reduce the temperature of the gas, as you'd expect, the volume will decrease, right? Now, the thing is that in practice, if you cool your gas to a sufficiently low temperature, the gas will be transformed into a liquid. So therefore, it won't be a gas anymore, and therefore, gas laws will not apply, right? So what was done was that, okay, since we know that it will be a liquid if you cool the gas to a sufficiently low temperature, the question that was asked was, okay, what if the gas could remain a gas at those low temperatures? What would happen if you extrapolate the line, right? So basically, even though we know that it won't be a gas at those low temperatures, what if it could be a gas at those low temperatures? Well, according to what the plot predicts that if the volume, if the gas is cooled to a sufficiently low temperature, then the volume of the gas, if it were to exist as a gas, would contract to zero. And it would contract to zero at this point right here, which would be minus 273 degrees Celsius, right? And that basically was set to be equal to 0 Kelvin, and that's how the Kelvin scale was established, right? So that's basically tantamount to moving this axis here, right here, I mean to the left, to get this plot right here, right? So basically, what this is suggesting is that if the gas were to exist as a gas at those low temperatures, then basically the particles would just simply collapse into, and I think I've seen this term in some textbooks, a perfect crystals, where there's no vibrational motion, no rotational motion, no translational motion. Basically, it will have no kinetic energy whatsoever, all right? So that's basically where we get the lowest possible temperature from. One thing you need to recognize is that, last time I checked, nobody has been able to achieve, experimentally speaking, 0 Kelvin, all right? And for some theoretical reasons, 0 Kelvin is basically impossible to achieve. And therefore, as a result, no one has been able to actually observe the collapse of any substance into that, single perfect crystal, so to speak. Okay, so let's look at this example. It says a balloon indoors where the temperature is 27 degrees Celsius has a volume of 2.00 liters. What will be its volume outdoors where the temperature is minus 23 degrees Celsius? So this is obviously a Charles law question. V1 over T1 is equal to V2 over T2. And what we need to find is V2, right? So basically to find V2, what we will do is multiply both sides by T2, right? So the T2s will cancel out there. So V2 will now be equal to V1 over T1 times T2. So it's all a matter of putting the numbers in. However, you're given temperatures here in Celsius. And remember, this law says that the temperature has to be expressed in Kelvin. So therefore, what I'm going to do is convert the 27 plus 273. So this would be 300 Kelvin. This would be T1, which would be 300 Kelvin. And then for minus 23, so that's 273 minus 23. So this would be T2, which is equal to which would be equal to 250, I'm sorry, Kelvin, all right? So now we have to put the numbers in. So V1, which is 2.00 liters, is equal to 2.00 liters multiplied by T2, which is 250 Kelvin, divided by T1, which is 300 Kelvin, all right? So 2 times 250 divided by 300, and according to my calculation, this works out to be 1.67, and the units will be liters because the Kelvin values will cancel out here and here, all right? Okay, any questions about this one? Any questions? Any questions? Yes, sir.
Can it also be milliliters too, or will always be liters?
Well, yeah, you could express it in milliliters, and I'm glad you raised that question because it doesn't matter what the volume units are. Again, for the same reason that I mentioned in the case of Boyle's law, as long as the volume units are the same on both sides, V1 and V2. So it could be milliliters, it could be liters, it could be literally any volume units. It could be gallons, it doesn't matter, right? But the temperature must be expressed in Kelvin. The temperature for T1 and T2 must be expressed in Kelvin. So if you're given a question like this, and you're given the values of the temperature in Celsius, you have to add 273 to it to get the corresponding value in Kelvin, and then you plug it into the equation, all right? All right, okay, what next? Okay, the next law is Avogadro's law, which is the law that describes the relationship between the moles of a gas and the volume. And here is the law in words. At a fixed temperature and pressure, the volume of a gas is directly proportional to the amount of gas in moles or to the number of gas molecules, right? So one way of expressing it is volume is directly proportional to the number of moles, or volume is equal to a constant times the number of moles, or the volume divided by the number of moles equal to a constant, or V1 over N1 is equal to V2 over N2. All right? So that's basically the relationship between the volume of a gas and the number of moles as described by Avogadro's law. Okay, so this brings us now to something that you would have met before in your previous chemistry experience, this whole concept of standard temperature and pressure, right? Because temperature and pressure affects other variables when it comes to gases, like volume and so on. In order to make meaningful comparisons between different substances, different gases, what we can do is adopt one particular value for temperature and another particular value for pressure as standard values, and therefore based on the result of other measurements for comparing two or more gases, we can make meaningful comparisons. So basically, standard temperature and pressure is defined as 0 degrees Celsius, which is 273 Kelvin, and 1 atmosphere pressure, which is the same thing as 760 millimeters mercury. Okay, so that is what we mean by standard temperature and pressure. Okay, why is this thing? Okay, now that brings us to another definition which you should have met in your previous chemistry experience, molar volume, right? By definition, the molar volume of anything, but we're going to apply it to gases here. The molar volume of a gas is the volume occupied by 1 mole of that gas, right? That's the definition of molar volume. And it turns out that under STP conditions, the molar volume occupied by an ideal gas is equal to 22.4 liters, right? So 22.4 liters is the volume occupied by 1 mole of an ideal gas, all right? And we can actually prove this mathematically, but that's for later on, all right? So some very important concepts that you need to remind yourselves of when it comes to solving certain problems later on. Okay, another law we're going to talk about is what is known as Gay-Lussac's law, which describes the relationship between the pressure of a gas and the temperature. And according to this law, at a fixed volume of gas and the amount of gas being also fixed, the pressure of a gas is directly proportional to the temperature expressed in Kelvin. So again, you see some ways of expressing the relationship between pressure and temperature. Pressure is directly proportional to the temperature, or pressure is equal to a constant times the temperature, or pressure over temperature is equal to a constant, all right? Or, as I'm going to write up here, P1 over T1 is equal to P2 over T2. Again, the temperature must be expressed in Kelvin. And again, the pressure units, doesn't matter what they are, as long as they're the same on both sides. All right? Now, so let's look at this problem right here. It says calculate the volume occupied by 4.11 kilograms of methane gas, and it gives you the formula, at STP. So the first thing I would do is start off with the 4.11 kilograms of methane, and I will convert that to grams. All right, so 1 kilograms of methane would go down here, and 1,000 grams of methane would go up top. All right, then the next step would be to convert from grams of methane to moles, which means we're going to need a molar mass. That's why they gave us the formula. So 4 times 1.008 plus 12.01. Okay, so according to my calculation, the molar mass of methane is 16.04 grams of methane for every 1 mole. Oh, shoot, I need to change that. I need to flip this. So I need to put 16.04 grams of methane below. And up here, I'm going to put 1 mole of methane, all right? So that this unit cancels over that unit. Then the next step is to go from moles of methane to the volume, which is what the question is asking for, right? Now, what's important for us to solve that is to recognize that the question says that the conditions are STP conditions, right? And because the conditions are STP conditions, we already know that under STP conditions, 1 mole of any gas will occupy a volume of 22.4 liters. So we can represent that here in this conversion factor, where we put 22.4 liters of methane above and 1 mole of methane below. So that would be the setup. So basically, all we have to do is crunch these numbers, 4.11 times 1,000 divided by 16.04 times 22.4. And according to, okay, so this I have to round off to 3 sig figs. So according to my calculation, this works out to be 5.74 times 10 to the 3 liters of methane. And that's how that is done. All right? Any questions about this one? Any questions? Any questions out there in Zoom? Okay, I take your silence to mean that you completely understand what's going on. All right. So what next? Let's see here. Okay, so we have learned about 3 laws so far. One that relates pressure to volume, one that relates volume to moles, and the other one that relates pressure to temperature. All right? And that is what is represented by these 3 equations right here. All right? So this is Boyle's, this is Charles, and this is Avogadro's law. All right? So basically, we can combine these equations here to end up with this equation right here. P1 V1 over N1 T1 equals to P2 V2 over N2 T2. Now, assuming that the amount of gas moles is fixed, this can be simplified to P1 V1 over T1 is equal to P2 V2 over T2. Right? So this is if N1 is equal to N2, all right? So in most textbooks, you're going to see this expressed as being the combined gas law, all right? Okay, so that's the combined gas law, which we can use to solve this problem. The question says the flask pictured in figure 0.11 contained oxygen, the one on the left at STP and the one on the right at 100 degrees Celsius. What is the pressure at 100 degrees Celsius? So they're asking for the pressure here, right? So the pressure over here is 1.00 atmospheres because it's STP. So basically, we can use the combined gas law to help us to solve this. The combined gas law is P1 V1 over T1, over T1 is equal to P2 V2 over T2, right? Now, in this case here, because it's the same flask, that means that V1 and V2 would be the same, right? So therefore, we can cancel these two. So you're going to end up with P1 over T1 is equal to P2 over T2. And then, to solve for P2, we rearrange this to get P2 will be equal to P1 over T1 times T2. So it's all a matter of plugging the values into this equation. Now, P1 is 1.00 atmospheres. T1 is standard temperature, which is 273, times T2, which is 100 degrees, which is the same thing as 373 Kelvin. So I'm going to multiply by 373 Kelvin, and that's it. So let's see what this gives. 1 times 373 divided by 273. And according to my calculation, this works out to be equal to 1.37. and the units will be atmospheres because the Kelvin units will cancel out there and there. All right. So that's basically how that is done. Any questions about this one? Any questions? Okay. Oh, there's an extra question being asked here. Let me clear this so that we can see what this question is asking for. It says, what pressure would be exerted if this were transferred into an oil bath at 200 degrees Celsius? Well, that's very simple because basically T2 in this case would be equal to 200 plus 273, so that's 473 Kelvin, right? So therefore, going back to the equation for P2, which would be P1 over T1 times T2. So P1 is 1.00 atmospheres times T2, which in this case would be 473 Kelvin, all divided by 273. And let's see what that gives. So that's basically 473 divided by 273. So the answer I got is 1.73 atmospheres. All right. And that's how that is done. All right. Any questions about this? Any questions? Any questions? Okay, so we can further combine all the gas laws, taking into account the number of moles. So this is a summary of all the gas laws that we have covered so far. And you'll notice that in each of these cases, we have to hold two things constant, right? So basically, what if everything changes? What if the pressure, volume, number of moles, and temperature changes? Then basically we can combine all of these into this equation, which is known as the ideal gas equation. PV over NT is equal to a constant, which is known as the molar gas constant, symbolized by the letter R. All right? And this is, and this is showing you what the value of R is, right? R has a value of 0.08206. For all purposes, we'll just run this off to 3 sig figs, right? So that would be 0.0821 liters atmospheres over mole Kelvin, right? In most textbooks, this is basically how it is expressed. Just a different way of showing the same relationship. And basically, you have to be careful about the units that you're going to use for the different terms, right? So in this particular case, based on this value of R, P would be expressed in atmospheres, V would be in liters, N would be in moles, and T would be in Kelvin, all right? But if you're going to use some other units for these variables, then a different value of R must be used. And that's what the next slide is going to show you. So if P is in atmospheres and all the other units are the same as I showed you before, then this would be the value of R. However, if you switch from P being expressed in atmospheres to P be expressed in torrs, then this would be the value of R, right? And furthermore, if you switch from torr to pascals in the case of P, and then the volume is switched from liters to meters cubed, then this would be the value of R, right? And later on, we're going to use this value of R in some other situations, right? But for most purposes, especially with respect to the ideal gas equation, this would be the value of R that you're going to use, all right? Okay, so let's look at this question here. This question says, what is the pressure exerted by 0.508 moles of oxygen in a 15.0 liters container at 303 Kelvin? And this is obviously an ideal gas equation. In this case, the question is asking for P. So therefore, based on the ideal gas equation, we can write down that P is equal to nRT over V. And it's all a matter of plugging the numbers in. So N is 0.508 moles times R, which is 0.0821 liters atmospheres over mole Kelvin, times T, which is 303 Kelvin. And then we divide all of that by the volume, which is 15.0 liters, right? So the mole units will cancel out, the Kelvin units will cancel out, and the liters units will cancel out. So therefore, your final answer would be expressed in atmospheres. So it's all a matter of crunching these numbers, 0.508 times 0.0821 times 303, and then we divide by 15, and according to my calculation, this works out to be equal to 0.842 atmospheres, and that's basically it, all right? So whenever you're doing these type of calculations, make sure that you include the units as a part of the whole setup so that you can see how some of the units will cancel out, so you end up with your answer expressed to the specific correct units, all right? Any questions about this one? Any questions? Any questions? All right, so here's another one. So in this case, they're asking for the volume. They gave you the mass, they gave you of the gas, and they gave you the formula for the gas. They gave you the pressure in torr, and they gave you the temperature in degrees Celsius, all right? So again, it's an ideal gas equation, but this is a bit more complicated because you have to do some unit conversion. So just to remind us of what the equation is, it is PV is equal to nRT, but what we need to find is V. So V would be equal to nRT over P, all right? So N, what is N? The moles, right? We're not given the moles, we're given the grams. So what we need to do is convert the grams of ethane to moles. So we need a molar mass of ethane, which is 2 times 12.01 plus 6 times 1.008. So according to my calculation, the molar mass of ethane is 30.07 grams of ethane per mole, right? Then we multiply by R, which is 0.0821 liters atmospheres over mole Kelvin. Multiply by the temperature. Now what's the temperature? 18 degrees Celsius, but we have to convert that to Kelvin. So 18 plus 273 would be equal to 291 Kelvin. And then we divide all of that by the pressure, which is 720 torr. But we have to convert that to atmospheres. So 1 atmosphere over 760 torr would be the conversion factor that you would use to carry out that conversion, all right? So we can see that the grams unit will cancel out, the mole units will cancel out, the Kelvin units will cancel out, the torr units will cancel out, and the atmosphere units will cancel out. So the only unit remaining would be the liters unit, right? So let's do the calculation. 16 divided by 30.07 times 0.0821 times 291, and then divide that by 720 divided by 760. And according to my calculation, now this would have to be rounded off to 2 sig figs. So according to my calculation, this works out to be 13 liters. And that's how that is done. All right? Any questions about this? Any questions? No questions? All right. I think I have another example here. Oh, no, before we get to the other example. All right, now we can actually use what we have learned, namely the ideal gas equation, to determine some other things about gases. For example, we can determine the molecular mass of a gas, all right? So this would require us to do some manipulation, algebraic manipulation of the ideal gas equation, all right? Now, in order for us to do that, what we're going to do is we're going to let uppercase M represent the molar mass of the gas, and lowercase m represents the mass of the gas in grams, all right? So if that is true, if uppercase M is the molar mass and lowercase m is the mass in grams, then the relationship between these two is what you see here. The molar mass is equal to the mass in grams divided by the moles, all right? Or we can rearrange it to get an expression for n, the number of moles, which would be lowercase m, which is the mass in grams, divided by uppercase m, which would be the molar mass of the gas, right? Now it turns out that we can rearrange the ideal gas equation to get an expression for n as well, right? N is equal to PV over RT. So we have n is equal to this, n is equal to this, which means that these two expressions are equal to each other, right? So we can say that M over M, or I should say lowercase m over uppercase m is equal to PV over RT. And then we can rearrange this to get an expression for uppercase M, which is the molar mass, right? So if we solve for the molar mass, that would be equal to M, which is the lowercase m, times R, times T divided by PV, all right? And basically, this here is what you use to calculate the molar mass of a gas. If you know the mass in grams, if you know the temperature, you know the pressure and the volume, and of course, R is always constant, then that would, when you put those numbers in, that would give you the molar mass expression, or the molar mass of the gas in grams per mole. And remember, we said this from, which chapter was it? I think the second chapter. Remember we said that the molar mass and the molecular mass are both numerically the same, right? So basically, if you know the molar mass, which is expressed in grams per mole, then the molecular mass would be the same number expressed in AMU units, all right? Okay, so based on this equation, we can apply this to solve certain problems, such as this one here. And again, this is something that I was recording, so I'm just going to use what I have written here. So this question says that if 0.550 grams of a gas occupies 0.200 liters at 0.968 atmospheres and 289 Kelvin, what is the molecular mass of the gas, right? So this is the equation that we're working with. It's all a matter of plugging the numbers in. So for the mass, that's 0.550 times R, which is 0.0821 liters atmospheres over mole Kelvin, times T, which is 289 Kelvin, and then we divide by the pressure, which is 0.968 atmospheres, times the volume, which is 0.200 liters. So we plug these numbers in, and you'll see that the gram units will not cancel out. In fact, the units that will cancel out would be the liters, the atmospheres, the Kelvin units. The only units that won't cancel out would be grams over mole, right? So that's why we end up with grams over mole here. And when I did the calculation, I got 67.4 grams per mole. But remember now, the question is asking for the molecular mass. So that's why I have to add an extra line here to say that the molecular mass is 67.4 AMU, all right? And that's it. That's how you solve this particular problem, all right? Any questions about this one? Any questions? Any questions? Okay. Again, this question is asking for pretty much the same thing as before. The numbers are different. And also, it's more complicated because you have to do some unit conversions. So again, you're using the same equation. They gave you 100 degrees for the temperature. They gave you the pressure, 755 torr. They gave you the volume, 185 mils. And they gave you the mass, which is, in this case, 0.523. So now we're going to plug the numbers in. For M, that's 0.523 times R, which is always 0.0821, times the temperature. Now the temperature given was in Celsius. We have to convert that to Kelvin. So that is 373 Kelvin. And then we divide by 755 torr. But we have to convert that to atmospheres. So that's why we multiply by 1 atmosphere over 760 torr. And then we multiply by 185 mils, but we have to convert that to liters. So that's why we multiply by this conversion factor. So that's basically the setup. And when you do the number crunching, you're going to end up with 87.7 grams per mole. That would be the molar mass, which means that the molecular mass would be 87.7 AMU. And that's basically it. That's how that is done. All right, so pretty much similar to what we did before, but there's an added complication in that you have to convert, well, in this case, you have to convert the torr units to atmospheres, and you have to convert the milliliters to liters. Okay, any questions? Any questions about this? Okay. One more thing I want to talk about before we get to your next assignment. We can also determine another quantity concerning gases, and that would be the density. Now, what we're going to use is the equation that we have been using in the past two problems, which is this equation right here. Now, if you remember, by definition, density is equal to mass over volume, right? So basically, in this equation, if you look at this equation carefully, you see that you have mass right here, right? And you have the volume right here, right? So basically, if you can isolate M over V in terms of everything else, you'll get an equation for the density, right? And that's what is done right here. M over V is equal to MP, uppercase MP, divided by RT, and that expression would give you the density. So therefore, this is the equation that you can use to calculate the density of a gas, right? So if you put the numbers in here, basically you're going to end up with your density expressed in grams per liter. And based on this equation right here, you can see some interesting relationship between different terms. For example, you can see that the density is directly proportional to the molar mass, everything else being the same, right? So basically, if you have two gases and everything else is the same, the temperature and pressure is the same, the one with the higher molar mass would be the one that's more dense, right? Or if you have two gases where the pressures are different, everything else being the same, then the pressure, the one with the higher pressure, will have a greater density. And then down here, as far as the temperature is concerned, the gas with the higher temperature will have the lower density, all right? Because there's an inverse relationship between the density and the temperature, right? So that's, you know, those are just some interesting relationships you can identify between the density and the different terms, pressure, molar mass, and temperature. Okay, so here is another example that I was recording. It says calculate the density of methane gas. They gave you the mass. They gave you, what did they give you? They gave you the temperature, they gave you the pressure, they gave you the formula. You're going to use the formula to determine the molar mass. So this is the equation right here. The molar mass from the formula is 16.04 grams per mole times the pressure, which is 0.978 atmospheres, divided by R, which is 0.0821, times T, which is the temperature in Kelvin, which is 298. You add 273 to this to get 298, and you put the numbers in, and this would be your result. The density will equal to 0.641 grams per liter. All right? Okay. Any questions about this? Any questions? And here's another example. Now, in this case here, they're asking for the pressure. They gave you the density, they're asking for the pressure, they gave you the temperature, right? So we're going to use the same equation here, but what I'm going to do is rearrange this to solve for P. So therefore, P is equal to dRT over M, and then I just put the numbers in. Now, the density is given as 1.50 grams per liter, multiplied by R, which is 0.0821, times the temperature, which is 25 degrees Celsius, which is the same thing as 298 Kelvin, and then divide all of that by the molar mass of oxygen, which you can get from the periodic table. 2 times 16, that gives you 32.00 grams per mole, and then you do the calculation, and I got, as an answer, 1.15 atmospheres. All right? So that's how that is done. Okay, so before we move on to gas stoichiometry, I'm going to give you now assignment number 5 to work on. Oh. There you go. And this is for you. And for you guys out there in Zoom, I am going to now publish assignment number 5. So let me go here. Let me go here, files. And then assignment number 5. Okay, so I've now published assignment number 5, which is this right here. So I want you guys to get started on questions 1 through 7. Right, so you should be able to do questions 1 through 7 based on what we have covered so far in lecture. Yep.
For number two,
Number two.
yeah. Do
Okay.
we need density?
No. Basically, it's kind of similar to the example that I showed you when it comes to closed and open end manometer. All right. Hold on, let me see. Let me. No, okay. The question says, if the atmospheric pressure is 0.975 atmospheres, what is the pressure of the enclosed gas in the left arm? So in each of these cases, you're trying to find the pressure of the gas on the left side, right?
Mhm.
Now, in the case of the first one, this end is sealed, right?
Yeah.
So therefore, the pressure of the gas here would be equal to the height difference between the two, which would be 45 millimeters mercury, right? And that's it. But in this case, remember now you have the barometric pressure acting down here, right? Now, because based on the difference in the mercury levels, we can see that the pressure of the gas trapped on the left side will be equal to the barometric pressure plus H, which is the 78 millimeters mercury, right? So basically what you'd have to do is, to calculate the pressure of the gas, you're gonna add 975 atmospheres, but you have to convert that to millimeters mercury. So 1 atmosphere here, 760 millimeters mercury, and then you add that to the 78 millimeters mercury, and that's where you get that. You see what I'm saying? So the pressure of the gas here would be equal to the pressure exerted by the atmosphere plus the H. So that's why we end up with this equation right here, right? The P bar is 0.975 atmosphere, right? That's what is given here, right?
Yeah.
So that's why I have this here. But I have to convert this to millimeters mercury because I have to add it to the 78 millimeters mercury, right? And then you work that out. So let's see. 0.975 times 760, and then that gives you, according to my calculation, that gives you 741 millimeters mercury. And then I add that to the 78 millimeters mercury. So plus 78. So according to my calculation, this works out to be 819 millimeters mercury. And that's what that is done. Now for this one, it's the reverse, right?
Yeah.
Basically, in this case, let me just write it up here. In this case, the barometric pressure will be acting here again, right? So in this case, P bar is equal to P gas plus H. So to get P gas, that will be equal to P bar minus H. So that would be 741 millimeters mercury minus H, which in this case is 76 millimeters mercury. So let me see what that gives. 741 minus 67. So according to my calculation, this works out to be equal to 674 millimeters mercury. And that's how you do that. Yes.
For number 6, is it 278 HG?
Hold on, number 6.
Yeah.
Let me get rid of this here. If you have a gas at 453 millimeters mercury with a volume of 700 mils and a temperature 20, what would be? Okay, so what are you asking?
Is it 278 HG?
Oh, yeah, that should be millimeters mercury. Yeah. Yeah. That is obviously a typo. Okay, gonna stop here for today. So make sure you do all the questions I said you should do, and then we're just going to continue. Oh, before I forget, so your test tomorrow, right, will be based on chapters 1 and 2. And I sent you this morning your assignment number 2 graded. And I've posted the answer key as well, so you can use those to help you to review. And I think I posted some past test keys as well. So all that should help you to prepare for your test tomorrow, right? So the first hour and 15 minutes of the class will be the test time, and then after that we'll just continue our discussion of gases. All right. So, and I'll be available today in my office from 1 to 5 if you have any questions that you want to ask. All right. All right, so that's it, folks.
For the open system for lab, the assignment, if you want us to take records of that as well.
Yes, and submit it online, yeah. Make sure it's a PDF, folks.